Welcome everyone. You are joining us for measuring long wavelength lasers with infrared cameras, pyroelectric scanning-slit sensors, and wavelength conversion apparatus. This webinar is presented by Ophir and hosted by us at Photonics Media. Today you're going to hear from Kevin Kirkham, the Senior Manager of New Business Development from Ophir at MKS Instruments. He has over 30 years of experience in laser diagnostics and quality assessment. Prior to working at MKS, he was product manager at Coherent Inc. and regional sales manager at Molectron Detector. In this session, Kevin is going to talk about the types of measurement tools available for long wavelength sources and help determine which tools are appropriate for different applications. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin, and you will be able to access the recording of this webinar online after the event. You will get links to that recording in your email inbox. So with nothing further from me, I'd like to welcome Kevin Kirkham. Welcome.
Good morning, everyone. Thanks for joining. This is Kevin. Today we are going to be talking a little bit about IR laser beam profiling solutions. By IR lasers, we're referring to the spectral range between 2 and 30 microns.
I'm sorry, Kevin, we're not seeing your screen right now.
I clicked on your...
Let me try that one more time.
Now?
I'm not seeing it, but okay, now I can see it. Sorry about that.
Okay. Let's see. So we're talking about, in this case, IR refers to the spectral range of 2 to 30 microns. Today's discussion will not include anything related to standard fiber or YAG lasers, nor will the presentation include InGaAs cameras or phosphor-coated cameras for that 1 to 2 micron range. Specialized cooled thermal imaging technologies such as Mercad telluride and INSBE will also be left out of this discussion, as I couldn't find any commercially available laser beam profiling systems that employ these cameras, although sometimes they are used in custom systems. So when we talk about laser beam profiling, we're talking about the cross-sectional intensity distribution of light within the laser beam. By sensing or mapping this information, a lot of different qualities regarding the usefulness of the laser can be determined. So the early days of CO2 lasers that were used as workhorses for material processing applications, very large garden shed size 5 kilowatt lasers used for material processing were the behemoths of the day. Images of the laser's cross-sectional intensity distribution was often obtained by using a fluorescent screen pumped by UV or black light. This phosphor-coated plate would create the laser beam intensity would create a shadow on the screen. One of the very earliest applications for laser beam profiling was done in this manner. A small portion of the beam was picked off and diverted to a phosphor-coated, typically aluminum plate. The differences in the heat or power density would cause changes in the shadow that was the beam profile. So you were able to monitor the power density or radiance profile that the laser operator needed to know to determine if the laser was operating correctly. Here is the standard top hat or uniform laser beam profile. You can see the false color image as well as a 1D or slice through that image showing the relative intensity profile of the beam. So when we're talking about profiling lasers, the primary information that we're going to be obtaining refers to the mode or structure of the beam, whether it's Gaussian or bell-shaped, or maybe top hat or uniform, the location of the beam, the size, shape, and ellipticity of the beam. All of these parameters are typically numerically analyzed for quantitative analysis of the laser's performance. Once cameras were developed and other sensors, other techniques, commercially available apparatus became available to do these in a much more cost-effective and uniform way. Some of the earliest or most ubiquitous tools for profiling infrared lasers consist of burn paper and acrylic mode burns. And you can see by both of these images that the beam profile was either burned or melted into the burn paper or acrylic, showing the size and structure of the beam. So physical representation of the beam was readily available through these low-cost but potentially dangerous techniques. So the numerical analysis of the beam's profiling results include, again, mode, size, and location. Mode is typical Gaussian or bell-shaped distribution. Is the beam round? Does the laser have a uniform or top hat distribution, or is it a donut mode? Where is it? Is it stable? Is the beam location where you think it should be? And is the size conducive to the task at hand? So numerical analysis of beam profiling results include location or positional stability. That is the position of the beam, typically denoted by the beam centroid, over time. Beam movement can rise to the level of being unacceptable if the application requires it to be located or focused. Numerical analysis of the beam profile result includes average power, peak power, beam widths or spot sizes, including a number of different techniques to measure the beam size, percent of peak, or the D4 sigma statistical distribution are some of the most common. The divergence angle may also be obtained and once you quantify the beam size. Mode can affect the laser's focusability, or M squared, and the beam propagation characteristics may also be measured with some of these apparatus. Once you can move the sensor through the beam's propagation, along the beam's propagational axis. Ellipticity is also a major takeaway from the numerical analysis of beam profiling. Here you can see the ellipticity and the orientation of the major axis of the ellipse being measured in real time, or has been measured in real time. Divergence and other beam propagation characteristics are easily measured with commercially available systems in many ways. To measure divergence, some techniques rely on a lens of known focal length, while other techniques require that you take two separate beam widths from a known distance from each other, past the waist or in the far field. Another representation here of a commercially available beam profiling software product. This is the data ray software. So Mode, location, size, and divergence angle, along with other beam propagation characteristics, are easily measured with commercially available systems. So the systems we're going to be talking about today include microbiometer-based camera systems, scanning slits with pyroelectric sensors that will cover this 2 to 30 micron spectral range, pyroelectric cameras, phosphor wavelength conversion products, and as somewhat of an afterthought, thermal quad sensors, which are not really beam profiler, standard beam profiling systems, but share some of the characteristics of what you would typically obtain from a beam profile system. We'll go into that in a little more detail. So microbiometer sensors uses change in resistance of a micromachine pixel and measure the beam profile, or the changes in temperature across the beam. Vanadium oxide is the material of choice. These microbiometer cameras typically cover the 8 to 14 micron spectrum, but that is largely limited by the window material. Here the data array WinCam D, which features a 640 by 480 sensor, 8 to 17 micron pixel, and a 30 frames per second frame rate. Signal to noise of this particular system is roughly 1,000 to 1. These numbers, specs, are all from the manufacturers, so these are this is not my data, but these are the manufacturer's data. Again, the commercially available beam profiling software package provides things such as beam width at various clip levels, plateau uniformity, ellipticity, the orientation of the ellipse, and many other ways to image the beam using a false color display and a 2-dimensional and an isometric 3-dimensional type of display. Another tool that's available commercially is a Pyroelectric Camera. This camera is offered by Ophir Spiricon and features a 320 by 320 matrix, 80 micron pixels, with a 1 inch by 1 inch image area. Maximum frame rate of this particular camera is about 100 hertz. It interfaces via USB or gigabit Ethernet. Here's the image of the sensor that goes into this camera. It's uncooled. It's read out, it's a flip chip type assembly where the crystal is bonded to a CMOS readout IC. Pyroelectric sensors require interrupted signal. Typically it is read both in the heating and cooling cycles to increase the signal to noise ratio. These are solid state sensors, and again, come with beam profiling software packages that give you a false 2-color display, various results, including size and location, Gaussianness, uniformity, pointing stability, and many, many other determinations. Another tool that's available is based on a scanning slit. Here, microscopic slits mounted on a rotating drum attenuate much of the beam. So in many applications, additional attenuation is not required. In this case, a pyroelectric version of a scanning slit detector is required for the 2 to 30 micron spectral range. Scanning slit beam profilers are offered by a number of vendors, including Data-Ray, Thorlabs, Ophir, and Duma, but I believe only the Ophir product is available with pyroelectric sensors that can measure this spectrum. Here, scanning slit sensors benefit from very good spatial resolution and very good dynamic range. This particular sensor interfaces via USB and has about a 10,000 to 1 signal to noise ratio. Again, they come with a suite of software that displays the beam in various ways as well as calculates the results. A description of how the scanning slits work shows that while the energy is integrated in the axis of the slit, the information comes from the axis of the scan. So the scan direction dictates the information that's available, whereas the orthogonal axis of the slit integrates all the light in that axis. So instead of obtaining a true 2D map of the beam, you really have an X and a Y view. In this case, those views are put together to create a 2D image. Since the measurement plane or the slit or knife edge is easily defined, the laser beam distribution at a known location is easily possible. And this is very important when you're trying to determine where the laser system is coming to focus or just what is occurring at a specific point along the beam's propagational axis. Knowing where the measurement is taking place is often very critical to successful outcome of your measurement system. One of the very old techniques that I started speaking about is a phosphor plate that is UV pumped. The phosphor coated plate creates when the beam is impinged on, it creates a shadow or a visible beam profile where the hotter portions of the beam appear to be darker. As far as I've been able to determine, currently there are no commercially available products that quantify this phosphor image. However, Mackin Instruments does offer these plates and gives a good visual representation of the beam profile in a very straightforward way. Spiricon of Logan, Utah used to offer a product called the Mode Check. That product has since been discontinued. That used the same technology that was imaged by a CMOS camera, and then that image was analyzed for quantitative analysis of the beam profile. Current products offer no quantitative analysis, qualitative only. The spatial resolution of this type of imaging plate is approximately 80 microns, with approximate signal to noise ratio of 100 to 1. One of the nice features of this technology is that you can apply quite a bit of power, up to 30 watts continuously with some of the devices. So again, not a lot of attenuation is necessary depending on the brightness of the laser. Here's the mode check, again, that used the phosphor plate technology. A rotating wand sampled the beam, directing portions of the beam onto the phosphor plate, which was then imaged and analyzed. This product has been discontinued for a number of years now. As somewhat of an afterthought, I've included quad power sensors. These are not traditional beam profilers in the sense that they do not provide a 2D representation of the beam or a beam profile per se. However, they do provide other properties of the beam, including the intensity or power or energy, the location of the beam centroid, and that can be measured over time. And of course, these sensors are a traceable intensity sensor as well. They provide a depiction of the spot size. So in addition to the quad sensors, there's an additional sensor that is used to help determine the spot size. The PC software that you can see on the left gives you a representation of the relative size and location of the beam. A beam tracking display is also available, and this can be read out through either the PC or a handheld meter display. Since these are not traditional beam profiling products, I wasn't going to add them to this, but then when I got to comparing the different technologies, I found that they did provide some important aspects of beam profiling, so I did include them. One of the very unique properties of this technology is that no attenuation is needed. The entire beam is impinged directly onto the sensor, of course, the unfocused beam, and it benefits from a traceable intensity measurement in either power or energy. Again, the PC software displays position and power information. The sensor is extremely durable, requires no attenuation optics, and is also used, obviously, to measure power. And wrapping up, to wrap up and compare the technologies, the microbiometer, vanadium oxide microbiometers have very good spatial resolution, good intensity resolution, good temporal resolution, but require the most attenuation of any of these systems. Software is available, and it can be used to measure propagation characteristics of lasers, including M². The pyroelectric scanning slit also has very good spatial resolution and very good intensity resolution with the highest signal-to-noise ratio of any of these products. The temporal resolution is good, but many times attenuation is not required. You can impinge up to 100 watts directly onto these sensors, depending on the beam size. Approximately 20 hertz update rate. And again, as I said, the best signal to noise or the highest signal to noise ratio of any of the systems. Software is available, and they can be used for beam propagation measurements. Pyroelectric camera has good spatial resolution, good intensity resolution, and very good temporal resolution. It does require attenuation in most cases, as only about 1 or 2 watts can be impinged directly onto the sensor. Update rate of up to 100 hertz. And again, beam profiling software and beam propagation software is available. In the case of the pyroelectric camera, the beam propagation software is not automated as it can be in some of the other products. Phosphor wavelength conversion products, again, there are no commercially available quantitative systems, so there's no beam profiling software or beam propagation software available, but it is a good visual representation of the beam and has the lowest cost of any of the systems, any of these available systems. Approximately 1 hertz update rate, but relatively poor, good resolution, similar to the pyroelectric camera. The thermopile quad sensor, being primarily a power sensor or intensity sensor, has relatively poor spatial resolution, but fairly good intensity resolution, and no attenuation is required. Approximately 1 hertz update rate, and the signal to noise ratio is very difficult to obtain. It really depends on a lot of variables, including the intensity of the beam and the size of the beam. So that's my presentation. This is my contact information. Please feel free to reach out if you have any questions you would like to address to me directly.
Thank you very much. We do actually have time for a few questions before we close. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. All right, so my first question is, how much attenuation do I need to measure an infrared laser?
That is totally dependent on the technology that's being used. Anywhere from many, many orders of magnitude of attenuation to no attenuation at all with the thermopile. In most cases, cameras require at least a few orders of magnitude of beam sampling and attenuation. And those products are available from the systems manufacturer.
All right, thank you. This next question is, can I measure infrared and fiber lasers with the same equipment?
Yes, in most cases you can. With the possible exception of the microbiometer camera, all of these technologies will also see the 1 to 2 micron spectral range.
Perfect, thank you. This next one is, how much does an electronic beam profiling system for infrared lasers cost?
Typically, you can expect to spend between $10,000 and $30,000 for a complete system, depending again on the resolution, whether it's camera-based, scanning slit-based. The thermopiles are significantly less expensive than this, but again, I'm not treating them as purely a beam profiling system. They're more accurately a power measurement system with some beam profiling characteristics.
Thank you. This next question is, do you have adapters for fiber laser outputs?
Yes, the manufacturers typically provide some sort of apparatus to position a fiber in front of the camera or scanning slit sensor. But they need to be fiber specific in many cases, and I would suggest you contact the manufacturer for more information.
All right, perfect. Thank you. Everyone, if we have not already answered your questions, please look out for a reply from us later. If you do think of another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That's webinar@photonics.com. And just a final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive links to that recording in your email. I'd like to thank Kevin Kirkham from Ophir one last time and thank all of you for participating today. This webinar was presented by Ophir and hosted by us at Photonics Media. Thank you.